Well, robots like this have many applications. You can send them inside buildings like this as first responders to look for intruders, maybe look for biochemical leaks, gaseous leaks. You can also use them for applications like construction. So here our robots are carrying beams, columns, and assembling cube-like structures. I'll tell you a little bit more about this. The robots can be used for transporting cargo. So one of the problems with these small robots is their payload carrying capacity. So you might want to have multiple robots carry payloads. This is a picture of a recent experiment we did, actually not so recent anymore, in Sendai, shortly after the earthquake. So robots like this could be sent into collapsed buildings to assess the damage after natural disasters, or sent into reactor buildings to map radiation levels. One of the disadvantages of these small robots is its size. And I told you earlier that we may want to employ lots and lots of robots to overcome the limitations of size. So one difficulty is how do you coordinate lots of these robots? And so here we look to nature. So I want to show you a clip of Phenogaster desert ants in Professor Stephen Pratt's lab carrying an object. So this is actually a piece of fig. Actually, you take any object coated with fig juice, and the ants will carry them back to the nest. So these ants don't have any central coordinator. They sense their neighbors. There's no explicit communication. But because they sense the neighbors and because they sense the object, they have implicit coordination across the group. So this is the kind of coordination we want our robots to have. So when we have a robot which is surrounded by neighbors, and let's look at robot I and robot J, what we want the robots to do is to monitor the separation between them as they fly in formation. And then you want to make sure that this separation is within acceptable levels. So again, the robots monitor this error and calculate the control commands 100 times a second, which then translates into motor commands 600 times a second. So this also has to be done in a decentralized way. Again, if you have lots and lots of robots, it's impossible to coordinate all this information centrally fast enough in order for the robots to accomplish the task. Plus, the robots have to base their actions only on local information, what they sense from their neighbors. And then finally, we insist that the robots be agnostic to who their neighbors are. So this is what we call anonymity. So what I want to show you next is a video of 20 of these little robots flying in formation. They're monitoring their neighbor's position. They're maintaining formation. The formations can change. They can be planar formations. They can be three-dimensional formations. As you can see here, they collapse from a three-dimensional formation into a planar formation. And to fly through obstacles, they can adapt the formations on the fly. So again, these robots come really close together, as you can see in this figure 8 flight. They come within inches of each other. And despite the aerodynamic interactions with these propeller blades, they're able to maintain stable flight. So once you know how to fly in formation, you can actually pick up objects cooperatively. So this just shows that we can double, triple, quadruple the robot strength by just getting them to team with neighbors, as you can see here. One of the disadvantages of doing that is as you scale things up, so if you have lots of robots carrying the same thing, you're essentially effectively increasing the inertia, and therefore you pay a price. They're not as agile. But you do gain in terms of payload carrying capacity. So I want to leave you with one last application. The robots that play the video are completely autonomous. You will see 9 robots play 6 different instruments. Let's watch.